Hi, everyone. Can someone confirm that they can hear me, please? Anybody hear me? Oh, thank you. Okay, so these are the announcements that I put up the last few times. The only changes are that the SRTE participation rate is now up to 60%. So we're getting there. You need to convince about 50 of your colleagues to do the SRTE, and then the full credit for doing the mastering physics assignment will be assigned. There is a final homework assignment that is due tomorrow. It's a fairly short assignment covering the most recent material. Please don't forget about it. And there will be extra office hours during finals week, Monday and Tuesday from 2:30 to 3:30, and Wednesday and Thursday from 2 to 3. I'm not sure if I mentioned this last time, but I think I probably did. So quiz 3, the mean was 64. That gets boosted up to a 70%. So I think given that the previous exam had such a high mean, people are doing on average pretty well. So that's good. And I remind you that there's a final. It'll be on Thursday. I think the time is in the afternoon, but please check Canvas for the details. And sort of the composition of the final is listed here, but it's also on Canvas. Okay, so today I'm going to do a review, but really it's solving a bunch of problems. And I'll first just give sort of a very, very broad overview of what we've covered in this class. So in the first part of the class, we talked about light, basically. First, dealing with how light behaves when it's a wave and when it behaves like a ray. And when it behaves like a wave, we get interference, we get diffraction, depending on what kind of opening the light is passing through and what the wavelength of the light is. And when it's a ray, we could look at things like reflection and refraction, as well as what happens when rays of light go through lenses or hit mirrors. And then we saw, when we switched to talking about relativity, how simple ideas can lead to totally counterintuitive phenomena. And in fact, this also held when we talked about quantum mechanics. So for example, by requiring that the velocity of light is always equal to c in all inertial reference frames, that gave us, for example, time dilation. Told us that time is not an absolute quantity. The fact that particles have wave-like properties, which can be observed by sending particles through openings and seeing them interfere or diffract, that led us to some of the key ideas in quantum mechanics. Some of the things we've learned in particular are that time is not absolute, as I just mentioned, that energy and mass are equivalent. We've learned why atomic energy levels are discrete or quantized. We learned how the fact that particles have wave-like properties gives rise to the stability of atoms. Otherwise, atoms should basically all collapse on themselves if everything behaved classically. And that also led, the wave-like properties also led to the uncertainty principle for massive particles, because there's an uncertainty principle that's sort of intrinsic to the description of waves themselves. And finally, we talked about the basic form and the solutions of the Schrödinger equation. This underpins all of quantum mechanics, and it successfully describes, a wide array of quantum phenomena. We covered just, a smattering of those. For example, the hydrogen atom and all of the spectra that are produced by the hydrogen atom can be solved or predicted by the Schrödinger equation in gory detail. And we also talked briefly about the quantum mechanical phenomena called tunneling. And then I don't list it here, but we also sort of looked very briefly at some of the applications of quantum mechanics in atomic physics and in nuclear physics. So these and other similar ideas, which are really the fruit of basic research as opposed to applied research, form the foundation for lots and lots of modern technology. All right, so I just want to say before I start working on some problems, the problems that I chose are based on your responses to the survey that I circulated rather late yesterday. I apologize I didn't do that earlier, but I got a number of responses, so hopefully everyone will find this review useful. And I also have looked at the optional mini surveys at the end of Mastering Physics, and that all those things have informed the choice of the problems covered in the review. The problems are representative, but they're not exhaustive. There are a lot of things we covered in this class, and some of the topics that we did cover are not going to appear here in today's slides. I'll also further add that I'll be working through some of the problems in this rather long list of slides, and the ones that I don't get to, I'll be posting so you can look at them afterwards. It may help you as you're studying. Okay, so first problem is on refraction. And the idea is to figure out whether an expensive looking piece of jewelry is actually diamond or if it's cubic zirconia or just glass. And those three different materials have three different indices of refraction. So in order to determine this, what the material actually is, you shine a laser at its surface. So if this is the surface and you shine a laser with an incident angle of 15 degrees, so here's the laser light coming in. So this is air, and this is either diamond or cubic zirconia or glass. And then on the other side, the angle is 6 degrees. So it gets closer to the perpendicular line, the normal at the interface. Question is, what's this material made out of? And to solve this, we apply Snell's law, and we calculate what the index refraction is in the material where the light is refracting at an angle of 6 degrees. So that just boils down to solving for n sub r, the index refraction, in the denser material, and the index refraction in the air is just taken as exactly 1.0, and the angle there is 15 degrees, and the angle inside is 6 degrees. So if you put all those things together, you predict, or you measure, I should say, that n sub r is 2.48, and so you can conclude that it's diamond. Okay, any questions on that? Okay. So the next example is with mirrors, and the thing that's drawn in this figure here, it looks like a flat plane mirror, but it's just meant to indicate, whoops, a generic mirror. So it could be concave, so it could look like this, or it could look like this. It's just drawn like that as kind of a placeholder to tell you where the mirror is located. So the idea is we have a 2 centimeter tall object that's over here. So that's placed in front of a mirror, and there's a 1 centimeter tall upright image formed behind the mirror, 165 centimeters from the object. So this distance is 165 centimeters. So what's the focal length of the mirror? What kind of mirror is it? And to do this, we're going to need these conventions, which are on the formula sheet, which as usual will be provided when you're taking the final. So in order to solve this, we first observe that the image is behind the mirror, so it must be virtual, and therefore S prime is taken as a negative number. And we know that it goes from being 2 centimeters tall to being 1 centimeter tall. So the magnification is 1/2, and it's also upright, so it must be positive 1/2. So we know that therefore minus S over S prime must be equal to 0.5. And that tells us that 2S prime is equal to minus S. We also know that S minus S prime is equal to 165. And the reason I'm writing it that way is because I know S prime is a negative number. And I know this total distance here is 165. Given that we also know that there's a relationship that S is twice as large in magnitude as S prime, you can solve for S as 110 centimeters and S prime as minus 55 centimeters. And then you can figure out what the focal length is of the mirror by using the standard formula. And you see that it's a convex mirror. So it's a mirror that's going to look like this, which you might have also been able to tell from the get-go because concave mirrors, well, I don't know, it depends on how far away the focal point is and so on. But we know, since this is a negative number here, that this is a convex mirror. Any questions? Okay. So now I'm going to move on to relativity. And here's a question on time dilation. So the question reads as follows. There's a particular nucleus that has a half-life of 1.2 million years in the rest frame. So what half-life means is if you have, like a lump of radioactive material, and you measure how many atoms you have of this radioactive material, how long will it take for half of those atoms to decay? That's the half-life. You can figure that out even if the half-life is 1.2 million years without waiting for 1.2 million years to make the measurement, because a sizable number of those atoms will decay fairly early on, but you can tell from that decay rate how long it'll take for half of all the atoms to decay. So anyway, in this problem, which is a little bit contrived, in the rest frame of this material, you measure that the half-life of the nucleus is 1.2 million years. And then there's this rocket that carries a lump of this material, and it goes flying by at a speed of 90% of the speed of light. And so you watch the decay of the nuclei from using your X-ray vision or whatever. And so what half-life do you measure? So the approach to take to this problem is to think about where the proper time is measured. The proper time is abbreviated with this tau. And the proper time is measured in the rest frame of the event, whatever that event might be. In this case, the event is the decays of the nuclei of this lump of radioactive material. And so that's what's measured sort of on the rocket to be measured to be 1.2 million years. So 1.2 million years is going to go up here in the numerator in delta tau, and then we're going to figure out what delta t is, which is the half-life that you measure watching this thing go by. So if you put in those numbers, what you get is that you will measure, if you're watching the rocket go by, a longer period of time, 2.8 million years, which is consistent with the idea that the shortest time the clock ticks have at least amount of time between them in the proper reference frame. So this tells you that time is not an absolute quantity. In general, this work, and that identical clocks that are in motion with respect to one another will tick at different rates, and both are right. So there's no one that's right and the other's wrong. It depends on the relative velocities. Okay. So next, I have, this thing is labeled, this question is labeled as a concept question, but I'll just let you think about it and then I'll post the answer. I suggest you don't look at the answers, so they're in the slides here. So let's read through this. Oh, I see there's a question. So I thought that tau was for the time of the person that is moving. No, tau is the proper time. So that's the time that is measured when the event at the same coordinate in the reference frame at the beginning of the event and at the end of the event. So there's in other words, there's a clock, in this case, in the rocket ship, and that clock is being used to measure the decay length. So, sorry, the decay time. So the proper time is being measured by the clock on the spaceship because that's moving with the radioactive lump of material. And the radioactive lump of material is what is producing the events that are being measured. Okay, so for this concept question, the idea is you set off two firecrackers, so they explode at exactly the same time in your inertial reference frame. So you're in frame S. You observe delta T equals 0 in your frame. And then someone in inertial frame S prime moving at some velocity V relative to S. So for example, someone driving by in a car, what would they say compared to you, what you say about these two firecrackers? So I'll let you just think about this for a second, read through the answers. Okay, so the first answer, A, says that delta T prime is equal to 0, since they must also say the firecrackers exploded simultaneously. That's wrong, because simultaneity is relative. Just because you say it's simultaneous in one reference frame does not necessarily mean, and in fact in general means it isn't simultaneous in the other reference frame. They measure that delta T prime is not equal to 0. That's true. They will measure that. But they will also conclude that the firecrackers exploded simultaneously. And that's also not true, again, because simultaneity is relative. Delta T prime is not equal to 0, and they will conclude that the firecrackers did not explode simultaneously, but they'll be wrong. So this is correct, and this is correct, but this is not correct. They will in fact be right. So even though they're measured as simultaneous in one reference frame and not simultaneous in another, doesn't mean that either of those people doing the measurements are right or wrong. They're both right. Finally, delta T prime is not equal to 0, and they'll conclude that the firecrackers did not explode simultaneously, and both of you will be right. So that's correct. And finally, delta T prime equals 0. Well, that's wrong. So we can just, don't have to read the rest of that. So the answer, proper answer, correct answer is D. Okay. So next I'd like to do a question involving relativistic energy and momentum. So the mass of a particle is m, and in order for its total energy to be twice its rest energy, what does its momentum have to be? So for the total energy to be twice its rest energy, that means that E is equal to 2E0. That's the basic requirement. So under those conditions, what does that mean about the momentum? So if we set the total energy to be twice the rest energy, then we're going to have 4 E0 squared equals E0 squared plus PC squared. And subtract E0 from it, we've got 3E0 squared equals PC squared. Take the square root of both sides, and we'll have square root of 3 E0 equals PC, because we're trying to find out what the momentum is. And remember that E0 is just mc squared. So then we can cross out that c over there, cross out that 2 in the exponent, and you see that the momentum needs to be square root of 3 mc in order for the total energy to be twice the rest energy. Okay, there's a question in the chat that says, in the Ryan and Peggy example, you said that they both can't be right. So what was said there was we assumed incorrectly that they would both measure the events to be simultaneous. And when we made that incorrect assumption, we ended up with a logical inconsistency, namely that Ryan would say that light detector would glow red, and Peggy would say it would glow green. And they can't both be right about that. So then we relaxed the assumption that Peggy would also measure the two events to be simultaneous, and then everything worked out fine. Then everything was consistent. So in that case, they are both correct, because Ryan will say that they were simultaneous and Peggy will say they were not simultaneous. So they're both right, because it depends on which reference frame you're in that says, that determines whether or not events are actually simultaneous or not. Simultaneity is not an absolute quantity. Okay, so what this example we just worked through says is, first of all, that energy and mass are closely related. You know that from the famous E equals mc squared expression. And here I put a little 0 down there, a subscript on E, because to indicate it's the rest mass energy and not the total energy E. And we have to account for the close relationship between energy and mass for subatomic particles. For macroscopic particles of matter, it doesn't usually matter. The energies that are involved are considerable fractions of the rest mass of the particles, and so therefore you have to take into account the rest mass. In the case of most interactions that happen with tennis balls or whatever, the amount of rest mass energy in a tennis ball is so huge compared to the kinetic energy that a tennis ball might have, that we can ignore these relativistic effects for objects like tennis balls. Okay, the next question is on the photoelectric effect. And by the way, I'm going through these questions roughly in the order that they appeared in the course and in the textbook. So there's don't read anything else into the ordering of these questions. So the question reads as follows. The work function for a certain sample is 2.3 electron volts. And the stopping potential for electrons ejected from the sample by 7 times 10 to the 14 hertz electromagnetic radiation is what? So think physically of what's happening here. So we have light, which has some energy we're going to have to determine, and we can use these two expressions here in order to figure out what the energy of that light is that's hitting the sample. And that light is going to have an energy that's greater than what in order for any electrons to emerge from the metal? Can anyone tell me in the chat? What's the minimum energy of those photons coming in? Right, it's the E0, which in this case is 2.3 EV. So here, remember, E0 is the work function. So these photons have to have an energy of at least 2.3 electron volts in order for any electrons to come off. If they have slightly more energy, the photons, than 2.3, then that additional energy is going to go into the kinetic energy of the electrons that emerge from the illuminated metal. And then the question is, okay, with that little extra energy they have, how much stopping potential do we need, or how much potential difference do we need between the metal and the collecting plate in order to prevent those electrons, which have that little bit of extra energy they got from the photons, from reaching the other plate? All right, so the first step is to figure out what the energy is. And you can just run through the numbers there. It's 2.9 eV. So that means that when a photon hits an electron in this particular material with a work function of 2.3, there's going to be 0.6 electron volts left over. So that's going to be the maximum kinetic energy that any electron coming out of the metal can have. Some will have less than that. So if the electron is buried, a few layers, atomic layers underneath the surface, then even if a photon hits it with 2.9 eV and the work function is 2.3, the electron is going to lose some energy as it, makes its way out of the metal and emerges from the surface. So it'll have something less than 0.6 eV. The electrons that are right at the surface don't have to deal with that. So their kinetic energy is the maximum kinetic energy, and that's 0.6 electron volts. So if you want to stop an electron, so if this is the surface here, and we're shining photons onto the surface, and an electron pops off like that, and we have a, just draw this here with a, we put a voltage on here, and I want to make sure I draw it correctly. So we want this to be negative, like so. So what does this potential difference have to be between the metal over here and the collecting anode over here, in order to prevent these electrons, which have 0.6 eV of energy, from making it all the way over to the other side? And the answer is simply 0.6 volts. You just take the maximum kinetic energy in electron volts, which is 0.6 eV, and you just divide by the E, and you're left with the V. So that EV, electron volt, is really electron charge E times volts. So the potential difference you need is 0.6 volts in order to prevent an electron with an energy of 0.6 eV from making it all the way across. So there's a question here, what's the purpose of dividing KE max by E? We want to figure out what the delta V is, or the V stop. And so if you want to figure that out, you need to divide by E in order to convert from electron volts to volts. All right. Any other questions on this problem? Okay. So next, I'd like to do this problem on wave functions and probabilities. So there's this weird looking wave function here, a very artificial one, that looks like alpha x over L, from x equals minus L over here to plus L over here. And it equals 0 here elsewhere. So to the left of minus L and to the right of plus L, it's 0. How do the probabilities of finding the electron near, so within some very small delta x, of points A, B, C, and D compare to one another? So what do you have to do to this wave function in order to get these probabilities? Can anyone tell me in the chat? What do you have to do to a wave function get the probabilities. I give you a wave function. What do you do with it in order to calculate the probability? Right, so you square it. So we need to square this wave function, and we only have to do this graphically. We don't need to square this function here. We could, but you don't need to. So if we square this function, what we'll see is something like this, very roughly speaking. So these peaks over here will be at the same height, and it'll go to 0 in the middle. So now we can look at this and say, aha, well, at point A, around point A, there's going to be a pretty high probability. The next one looks like it'll be point D, and then B, and finally C. So A, D, B, C. So the answer should be C here. So the probability of finding it at A is greater than the probability of finding it at D, which is greater than B, and at C, there's going to be 0 probability of finding it. So here's a nicer picture of the same thing. And you could, of course, if you squared this function, psi of x squared is alpha squared x squared over L squared. And this is a formula for a parabola. And so, this thing here that I drew is intended to look like a parabola. It's not precisely one because I drew it by hand, but, a parabola with its minimum at 0, and it reaches, a maximum at x equals plus minus L. Any questions on this? Okay. By the way, the bars that can be interpreted as absolute value for the wave function actually mean more generally that if you have psi of x equal to some a plus bi, some complex number, that psi of x squared is equal to a plus bi times a minus bi. In other words, this psi squared is meant to be equal to psi of x times the complex conjugate of psi of x. So these absolute value signs are meant to be more general for when the wave function could be complex. All right, so next I'd like to talk about the infinite potential well. So this was sort of the simplest case for a potential that a particle might be in. And in this case, we have an electron in this one-dimensional well, which has 0 potential energy inside and infinite potential energy at the walls. So it goes between 0 and L, and then over here, the potential energy is infinite. And the particle has 2 eV of energy. So now what happens if the width of the wall, if the width of the well, sorry, is doubled? So this L basically goes to 2L. What happens then? Well, if you look at this expression here, what's going to happen if everything else is kept the same and we double L? What are we going to do to the energy? So N stays the same, H, 8, and M all stay the same, but L doubles. What's going to happen to the energy? Anyone tell me in the chat? Right, it's going to go down by a factor of 4. So if L goes to 2L, then that means that the energy is going to go to whatever it was before, divided by 4, because L is squared in the denominator. If you put a 2L in place of L, you're going to get a 4L squared coming out. So you basically have divided the 2EV that you had from this expression here. You can divide that by 4. So the correct answer will be 0.5 electron volts, because that's 2EV divided by 4. All right, here's another question on infinite potential well. Again, we have an electron that's confined to a one-dimensional region between 0 and L, and it's bounded by an infinite potential. So we're going to determine the probability of finding the electron in the n equals 4 state in between these two values of x. I see there's a question in the chat. Let me go back and explain this question again. So we had initially told that this is equal to 2 electron volts. And so this whole thing here is equal to 2 EV. So if I take that and I write n squared h squared over 8m times 2l squared, what I'm going to get is n squared h squared over 8ml squared. And there's going to be a 4 coming out here as well. So this thing here, that is 2 electron volts. And then I'm dividing it by 4. If I make the wall twice as, or the potential well twice as wide. So the 2 EV gets divided by 4, as shown here. Okay. So we have this potential from 0 to L, and we have the n equals 4 state, and we want to find the probability of finding the electron in the n equals 4 state in this region. So the thing to remember is that the n equals 1 state, has one antinode. So that's, right here, that's its antinode, the peak. The n equals 2 has 2 antinodes here and here. N equals 3 has 3 antinodes, and n equals 4, I'm not going to, well, I guess I should draw it. So here are the 3 antinodes. And so n equals 4 is going to look like this. I think I've thrown that right. So it's 1, 2, 3, 4 antinodes. Okay. So that is the n equals 4 state. That's what the n equals 4 wave function is going to look like. So let's take that n equals 4 state, that wave function, and square it. And what do we get? Well, we're going to get something. Now I'm just going to draw the n equals 4 wave function. So it looks something like this, the wave function. And if I square it, it will look like this. Four peaks. I didn't quite draw those exactly right, but I think you get the idea. And so the question then is, how much area is there between, so here's the midway point, that's L over 2. This is L over 4. So this is going to be L over 8 right here. And this will be 3L over 8 over here. We want to know how much area is in this region underneath those red curves. That will tell us the probability of finding the electron, if it's in the n equals 4 state, in between L over 8 and 3L over 8. So let me draw that more nicely here. Now you can probably see what's going on a little better with this. So again, it goes from 0 to L. And there are 1, 2, 3, 4 antinodes. And then we square that wave function and we get these 4 big peaks. And then we look in the region between L over 8 and 3L over 8. And we say, how much of the total area is underneath psi squared in between those 2 points on the x-axis? And you can tell just by symmetry arguments, the area, of course, say underneath one of these bumps, from here to here, is going to be 1/4 of the total area. And therefore, looking at half of the area under the bump, the first bump, and half of the area under the second bump is also going to give you 1/4 of the total area. So if we're at 1/4 of the total area, that means total probability of 1/4 or 25% of finding the particle in the shaded region in this figure. So again, the wave function squared tells you something physical. It tells you the probability of finding a particle. In the most general case, the first thing you would need to do to figure out what's the probability of finding the particle from given this wave function is normalize the wave function, so that if you then integrate its square between 2 bounds, you'll end up with something that can be interpreted as a probability. In other words, the maximum probability of finding the particle in any point in space has to be equal to 1. And so that's what the normalization constant tells you. In this problem, we didn't need to do that because we were just taking the ratio of the area in this pink region to the total area. And that gives us probability. So we could skip over that step of finding the normalization. In fact, we can skip over the step of actually writing down any wave functions, because there was a fair amount of symmetry. Any questions? All right. So next, the de Broglie wavelength. The basic idea behind a de Broglie wavelength is that just like light, when it's treated as a wave, behaves with wave-like properties when it goes through, say, a slit, a narrow opening. It can exhibit interference and diffraction. So can particles. And the reason particles can do that is because they themselves have a wavelength that describes them. And that's called the de Broglie wavelength, after the person who first proposed the idea. And so this question is a relatively straightforward one. What de Broglie wavelength is expected for a beam of electrons that have a non-relativistic energy of 100 eV? So remember that the de Broglie wavelength is equal to h over lambda. Sorry, the momentum is equal to, I should write this properly, sorry. So the de Broglie wavelength is equal to h over the momentum of the particle, and h is Planck's constant. So if the kinetic energy is 100 electron volts, that equals 1.6 times 10 to the minus 17 joules. And we're told this is non-relativistic, so we can set that kinetic energy equal to p squared over 2me. This is the same as 1/2 mv squared. But we're trying to work with momentum here because momentum appears in the expression for the de Broglie wavelength. Lambda equals h over p. But anyway, we can then solve for momentum. It's equal to the square root of 2 times the kinetic energy times the mass of the particle, the electron in this case. And then we just put that momentum down here in the denominator, put in the very tiny value of h, and we end up with 0.12 nanometers as the wavelength for these electrons. So if you had a beam of electrons with 100 electron volts of energy, then in order to get them to behave in a wave-like manner, they would need to see an opening that's roughly of this scale, so below a nanometer in size. And the things that have such small scales typically are like the crystalline lattice structure of solids. So in order to get electrons to behave like waves, you may need to send them towards a material and see what happens when they bounce off. All right, the next question is on tunneling. So the question just asks you to rank the tunneling probabilities for these 4 different cases. And I'm sorry that this is a little bit fuzzy. The 1 EV and the 2 EV and so on, those refer to the difference between the peak of the barrier and the total energy of the particle. So this is 1 EV in between here. And then the barrier width is shown down below. So the important quantities are 1, 2, 1, and 2 EV, and 1W, 1W, 2W, and 0.5W. The thing that matters, the tunneling probability, is given by this expression. So it depends on the width, W, and on the penetration depth, eta, which depends inversely on the difference, U0 minus E, which is basically this 1, 2, 1, and 2 EV quantity that's shown in these 4 different figures. Okay, so the best way to approach a problem like this is to figure out how the probability is going to depend on the 2 quantities that are presented. And so to do that, you should note that the thinner the barrier, the higher the probability. So if W is small, then this exponent will be less negative. So the probability will be higher. And if the energy difference between U0 and E is smaller, then eta will be larger. And then again, this probability, the exponent will be less negative. And so you'll get a probability that's larger. So there's a lot of things to keep in mind mathematically as you're going through this. But basically, the total probability is going to be proportional to the size of the barrier. So with a negative sign in front of it, and the square root of the difference between U0 and E, which is what these quantities here are giving you. So for case D, the barrier width is 0.5, and we're going to get a square root of 2 from the 2 EV difference, because we're going to have a 2 down here. And I'm just ignoring all the other factors, the H bar, the 2M, this factor of 2 here, because they're common. They're the same for all these 4 cases. So the ratios of these cases, or the proportionality of these cases one to the other, just depends on the 0.5 and the square root of the U0 minus E. So if we look at those quantities, we see that the smallest negative number is given in case D. And that's the reason I carried around the minus sign, just to remind myself that what I'm looking for is a negative number to be as small as possible. And so if you look at the 4 different cases, you'll see that D is larger than A, is larger than B, is larger than C, because D is less negative than A, which is less negative than B, which is less negative than C. Any questions? Okay. So the last one I'm going to do is the hydrogen radial wave function. And the idea here is to prove that the radial probability density peaks at the Bohr radius for the 1s state of hydrogen. And we're going to use this radial wave function that comes out of the Schrodinger wave equation to do this proof. The probability density, which is what you're trying to maximize, is given by 4 pi r squared times this the square of this radial function. And if you write that all out, you see something like this. You got some constants. So I don't know if that's easy to see. Let me just write it out. So that's what that equals. That's the probability as a function of r. Because we've multiplied it by the size of the spherical shell. And this peaks when its derivatives equal 0. So all I need to do is take the derivative of that expression, this here, and set it with respect to r, and set it equal to 0. And you'll get an expression that looks like this. And this thing out in front doesn't matter. And then you just have to solve for this piece, set it equal to 0. And you see that if you look at that carefully, the exponents cancel. And so you're left with r squared times minus 2 over ab equals 2r. And if you solve for that, you see that it gives you r must be equal to a sub b, the Bohr radius. And I don't know if you remember, but we had a plot of the probability. So this is for 1s. So this is the probability as a function of r. And this was at the Bohr radius right here. It had a peak right there. So that's what this proves, that's where that peak should be. Okay, thanks very much, everyone. Good luck on your finals. Hope you enjoyed this introduction to modern physics. I enjoyed teaching it in spite of the fact that I did it from my office at home. Good luck on all your finals and have a safe and relaxing break. I'll stick around a little bit longer if anyone has any additional questions. Bye-bye.
Hi, can I ask a question?
Yes.
So in the book, there was like a stop to think after the tunneling microscope. It says like a particle with energy E approaches an energy barrier height of like U sub 0 is greater than E. If U slowly decreases the probability that the particle reflects from the barrier. I'm confused why if U decreases, why is the probability going to also decrease? Because I thought if like the barrier, like I thought it's trying to overcome like that potential energy.
So it's asking what's going to happen if the particle reflects from the barrier.
Oh.
So we've been talking about is what happens when what's the probability that it will get through the barrier. So in the extreme case, if you have a barrier looking like this and the particle is coming towards it, okay, there's some probability it will get through.
Yeah.
If I make this barrier really tiny, then the probability that the particle will reflect off of that barrier is going to get small. And if in the limiting case where that barrier has 0 height, right, then there is no probability that it'll reflect because it won't be there.
Oh, so yeah, so you need that potential like energy in order to like keep that like the electron like within that confined area.
Well, the only way you're going to get, so this is the transmitted electron. The only way you're going to get it reflected is if it has something to bang into. And I'm speaking classically, but I think you get the idea. So as this barrier decreases in size, there's less and less there for the particle to bang into. And, and it'll be easier for it just to go straight through. And in fact, you know, in a limiting case where there's no barrier at all, you expect no reflection.
So like when it says in like the tunneling, how they're talking about how the energy lines on both sides of the barrier are going to be the same. So when it goes to the classically forbidden region, like, won't it always go through though? Like I know we set the barriers up, but like it's always going to go through at least like a little bit, right?
So if you look at, do you have the book in front of you on page
Yeah.
1169?
Yeah.
So there's a figure there, figure 4031. You know, it
Okay.
looks like this. It's got this high wiggle thing here. And then, okay. So what this is showing you is that there's some probability that the particle that's over here on this side will end up on the other side. That probability is proportional to the amplitude of the wave function on either side. So most of the time, what this particle on this side will do is basically bounce off. So it's just bouncing back and forth between this barrier, and presumably there's an infinite wall or something on the left. But some fraction of the time, it gets through, and then it's over here. The energy that it has is going to be the same energy that it had when it was to the left of the barrier.
Okay.
The fact that the wave function has a smaller amplitude indicates that the probability of the particle being on the right side of the barrier is smaller than it being on the left side of the barrier. It doesn't tell you anything about the energy. The energy stays the same.
Oh.
When the particle goes through the barrier, for a short period of time while it's in there, its energy does change. And in fact, conservation of energy is violated for a short period of time.
So why do they show the amplitude as like decreasing? Like what's the what is causing that amplitude to decrease?
So on one side, you have the probability of finding the particle. So let's say this is 0 and L. Getting kind of messy here. Hold on a minute. We got a different color. So we have 0 over here, and then this is at L. And I don't know, let's just say this is, I don't know, B. So psi that quantity squared tells you the probability of finding the particle somewhere between 0 and L. And this probability is to be compared with the probability that you get for the particle to be basically beyond B. And the fact that the amplitudes over here are larger than the amplitude over here to the right of B is a statement that, for example, the maximum probability of finding the particle at x greater than B is going to be smaller than the maximum probability of finding the particle between 0 and L.
I see. Okay, that's interesting. Because at first I thought, like, because when they were discussing at the beginning of the chapter, like the fact that like inside the classical box that they designed, like it's all like kinetic energy, and then outside it's potential. That's why, and how like the wavelength can like change, like as the wavelength increases.
Right, in like a finite potential well, you mean, yeah.
Right, so that's why at the beginning of the chapter, because of that, I thought that in like outside of the classically forbidden region, I thought we would see like the wavelength changing because like the energy was changing, I guess. Like as K decreases, the wavelength would increase.
Okay, so the presence of this barrier here is going to change the wavelength of the wave in between 0 and L.
Okay.
And consequently, the energy of the particle in between 0 and L, compared to the case where you had infinite potential on both sides.
Okay, but then it's like restored after, I mean, in a sense. Because like the wavelength doesn't change after.
Energy is conserved, so when the particle gets through to the other side, it'll have the same energy, whatever that energy was, that it had inside. And that energy is going to be some quantized value. And that energy will be reduced somewhat by the presence of this finite potential well.
Okay. And then like one other just like random question.
It has to be quick. I need to get ready for the next class, but go ahead.
Oh, okay. So, and just like like this whole scenario though, like what is the actual like situation of this? Like the electrons going through the barrier, is it like going to like another, like, you know what I'm saying? Like in like a real example of it, like where this is actually occurring.
So the real example would be the scanning tunneling microscope. So basically the particle between 0 and L in this diagram, that's the particle sitting on the substrate. And the particle on the other side of B is when it's jumped across this barrier, that's this potential barrier here, and made it up to the tip.
Oh, okay. That makes sense.
I'm sorry, but I really have to leave now to get ready for the next class. So if you have further questions, feel free to either post them in Piazza or send me an email or whatever. Okay?
Okay. All right. Okay. Thank you so much.
Thank you.